All right, good morning everyone. So I guess we can try to start. The plan for today is to try to cover the heat exchanger problem and then have our small exercise, and then I'm gonna try to cover something somewhat challenging for me. I had a kind of a big flow diagram that I was last year I was actually covering on the entire board, which is kind of, you know, flat and horizontal. So we will try to
Hocam kayda alıyor musunuz acaba? Chatten de biz.
hatırlattığınız için teşekkür ederim. Alıyorum. So that's a good point to remember. Okay, I started the recording. So in the second half of the course, we will try to cover that on our limited screen real estate with the tablet. So we will see how that will go. But in any case, I have something in my notes. So if our experience with the tablet is not that great, we can also I can share my notes with you, and I still need to share with you the last week's handwritten notes. So I will do that. All right. So let's maybe switch to our the last notes from our from last week's last course. Okay, so let's open that up. So let me first show you. I kind of had a trial. You know, we will try to cover something like this, which is just maybe 1/3 of the diagram. Okay, but we have the ability to zoom in and zoom out. So we will kind of try to go in and out of this figure. I will draw this from scratch. So this was just a trial to see whether I can do that. Okay. So here is the notes from last week. Let me remind you guys that essentially we started looking at a system called the heat exchanger. Okay, this system is primarily used for regulating the heat of a flow of liquid. Okay, so what's happening here is that an incoming liquid with a measurable but variable temperature T in, and there is a heater that we can activate, and then inside this is a well mixed liquid. So the heat from the heater is actually transferred to the liquid, and the aim is to be able to have a constant temperature, constant output temperature T at the output of that vessel. So obviously we need to somehow regulate, we need to activate the heater in a controlled way in order to affect what's going to be the output temperature. Okay, but the purpose of this system is to have a means to do that. Okay, so the aim of this system eventually is to have a constant temperature T at the output. And also in terms of the flow of liquid, the amount of liquid, the inflow rate has to be equal to the outflow rate, because we are not interested in the level of the liquid. The level of the liquid is supposed to be constant. Okay, so that's another problem that we studied, how to do that. But we assume for this problem that the level of the liquid is constant, therefore the volume of the liquid inside the tank is constant. Okay, so there is inflow of liquid with an variable temperature T in, and there is an outflow of liquid T with a temperature T, and we are interested in the dynamics of this system. That means how all the variables inside the system actually affects this output temperature T. Arkadaşlar, sesle vesaire herhangi bir sıkıntı var mı, yoksa her şey yolunda mı? Yusuf Erdem, sen en tepedesin, sen söyleyebilirsin. Mikrofon kapalı. Yusuf Erdem, burada mısın? İlhan Can, sen duyabiliyor musun beni?
Duyabiliyorum hocam.
Okay. Herhangi bir sıkıntı yok.
Yok, hayır.
Yusuf Erdem is no longer with us gibi bir durum var. AFK mıydı? Away from keyboard.
Evet hocam.
Okay. So these are the different variables that we defined with respect to this system. Do you guys have any questions about any one of the parameters of the system that we described at this point? All the variables are clear for everyone? All right. So, okay. So let's continue with our discussion in that case. Now, how do we come up with the dynamic equations? Remember that we will make use of the same concept of the conservation law. Okay, so we will do the same as we have done before for the conservation of mass. Now we will basically say the main conservation law is effectively that heat accumulation in the system has to be equal to the difference of the inflow of heat energy minus the outflow of heat energy. Okay, so heat accumulation, I mean, thermal systems like fluidic systems are very similar to electrical circuits. Okay, and we defined in our last lecture that we have so-called across variables and through variables. In the case of a heat system, the across variable is the temperature difference across a component and so on, and the through variable is the flow, the heat flow. So it's the heat flow rate. Okay, so in that sense, this system behaves in a very similar way to a capacitor in an electrical circuit. Okay, so if you have a capacitor and you have an inflow of current and an outflow of current, the charge accumulation will be equal to the difference of the inflow and outflow. Okay, so there will be a net charge that cannot go anywhere, so it needs to be accumulated inside the system. So this heat system is very similar in the sense that the volume of liquid inside the tank will be storing heat energy, and how much is being accumulated there is equal to the difference of how much heat is coming in and how much is leaving that volume. So in the same way as we have for the capacitor, heat energy accumulation basically means a change in the temperature. Okay, so this, if we call R as the heat flow rate, okay, we basically have C times dt of T over dt. dt of T over dt is basically the rate of change of temperature. And in this case, what we call C is the thermal capacitance. Okay, so I call this C in a way similar to the electrical circuit. So it's basically how much heat energy can be stored by the system. So this needs to be equal to R net. And R net, which is the net flow, is basically R in minus R out. So we will transform this basic equation into our final dynamic equation for this system.
Hocam buradaki T direkt şey gibi, voltaj gibi bu.
Exactly. The temperature difference here corresponds to the voltage difference in an electrical circuit, while the thermal heat flow directly corresponds to the current flow in an electrical circuit. Okay. Remember that likewise, as there is no absolute voltage, always all voltages are actually potential differences in relation to a reference point. Or if you're talking about a component, the voltage difference we are talking about is the voltage difference across the component terminals. Similarly, the temperature is also a relative quantity. It is always in reference to essentially a reference point. Okay, so it's the temperature difference which actually causes heat flow. Okay, it's not an absolute temperature, but a temperature difference. So if there is a temperature difference between 2 points, you know that there will be a heat flow between those 2 points in a way that the current is the result of a voltage difference. Okay. Any other questions at this point? Okay. So that means if the T is the rate dt of T over dt is the rate of change of the temperature. So let me write this again. T of T here is the temperature difference. So this is our across variable. And we also have R net being the heat flow. This is the true variable. Okay. So, and the liquid in the tank, liquid's volume in the tank is we can say, is the cause of thermal capacitance. Obviously, how much thermal capacitance we have is related with some more basic quantities like the liquid's volume, liquid's capability to store heat, depending on its material, like is it water or is it some other fluid, as well as its density. Okay. So now I'm going to try to write down our equation here. Basically, this thermal capacitance can be written in terms of these basic quantities like volume of the liquid, the density of the liquid, as well as the specific heat of the liquid. For example, if you think about car cooling systems, you know that there is a special liquid that is stored inside the thermal system. And this liquid is specially designed to be both resistant to freezing, but also in order to be able to store as much heat as possible, because it is supposed to remove the heat from the engine, and it's supposed to have it cooled in the heat exchanger. Okay, so volume of the liquid, the density of the liquid, and the specific heat gives us the thermal capacitance times dt of T over dt, our primary output variable of interest, is equal to R net, which is R in minus R out. Now I need to express what is going into this system and what is going out of this system in terms of heat energy. Okay? Can you guys tell me what are the sources of the input heat energy to this system?
The heater.
Who is speaking?
Özgür.
Özgür. The heater itself is a direct heat input, right? How much we activate the heater, okay? This is like an actuator in a system, right? We can turn on the heater, we can turn off the heater. That will depend. Even we can, most heaters are controlled in an on-off fashion, but there are heaters that can be controlled in an analog way or a continuously variable way. So this is like an actuator in the system, right? Is this the only heat input to the system?
Yukarıdan damlayan koyduğumuz liquid de var.
Yes, that is correct, right? Although that's not dripping, really, it's really flowing, despite my kind of sketch, okay? So there is a lot of fluid coming in, in fact, as much as the amount of fluid coming out, okay? So there is a constant flow of liquid in and out, and the incoming fluid has a certain temperature, so it's bringing in a certain amount of heat energy. Okay, so let's try to write down these two. And what is the source of the outflowing heat energy?
O akan vanadan aşağı giden.
That is correct, right? The outlet of the tank is liquid is going out, and liquid has a certain temperature T, so that carries out a certain amount of thermal energy with it. Okay, so we have two inputs of heat energy, two sources of incoming heat energy, and one source of outgoing heat energy. So let's try to write them down. Okay, let's start first with the incoming fluid from the top. So that's going to carry an amount of heat energy, which is again related with the capacity of the heat or the capacity of the liquids carrying heat energy. So it's going to be the flow Q times again the same kind of quantities, right? That means the density of the liquid coming in, the specific heat of that liquid times the temperature of the liquid. Okay, so this factor in the front has the flow rate, the density, the heat capacity, okay, the specific heat, as well as the temperature of the liquid. The higher the temperature, the more energy is coming in. The higher the flow, the more energy coming in. Okay, any questions here? Now we come to the heat carried in by the heater. So that's going to have essentially a parameter alpha. Alpha will be basically the heat transfer coefficient. Heat transfer coefficient. Okay, so that means what is the material in between the heater and the liquid? Is it a good heat conductor or is it a heat insulator? Obviously in this application it needs to be something that can very easily conduct heat, okay, so that the heat transfer coefficient will be a higher number. It's also related with the area of contact, okay, area of contact, clearly, because the higher the area, the more the heat has a chance to be transferred from one medium to another. And in fact, if you think about, for example, a car cooling system, again, engine cooling system, the radiator is actually specially designed to increase the area of contact as much as possible between the cooling liquid and also the ambient area, because we want to just get rid of the heat. Okay, and inside the engine there is a lot of channels where the liquid is passing through, so that it has enough area of contact with the engine to remove the heat from the engine. Okay, and also this transfer is related with the heat difference. So this is going to be related with the heater's temperature, Th of T, minus the liquid's temperature. So the higher the difference in temperature, the more heat will be transferred in between. Okay, it's like the current again. Okay, as the current is linearly proportional with the difference in the voltage, same goes here as well. So that these two are the two sources of the incoming heat energy. We also have the outgoing heat energy with a minus sign. The same flow rate Q, again the same density of the fluid, the same specific heat, because it's the same liquid coming in and out, and this time it really depends on what's the temperature of the outflowing liquid. So incoming energy comes in with the input temperature, and the outflow energy is going out with the regulated output temperature. All right. All right. So let us kind of rearrange this equation. So let me first, you see that we have basically the same variable here in both cases. So let me rewrite this. V rho Cp dt of T over dt will be equal to, again, first incoming energy, rho Cp T in of T, minus, we have two coefficients with a minus sign, so that's going to be Q rho Cp plus alpha F times T of T plus alpha F Th of T, the heater temperature. Okay, so you see that we have our differential equation variable T of T, and we also have T in of T and Th of T. Now these two variables, T in of T and Th of T, are kind of the two inputs to the system. Okay, so let me kind of rearrange that again. So what I'm going to do is put all the T variables to the left, and I will leave all the input variables on the right, and I will also scale with this term. So I'm going to divide everything by this term. So that's going to be V rho Cp divided by Q rho Cp plus alpha F times dt of T over dt plus T of T now, which is by itself, and that's going to be equal to a first term, Q rho Cp divided by Q rho Cp plus alpha F times T in of T, and plus alpha F over the same quantity, rho Cp plus alpha F times this time Th of T. Okay. Now let us call, in order to simplify things a bit, let us call this T1. You can actually call it C1 or C. It doesn't matter. if you kind of confuse this T1 with other T's, there is a lot of T's. So in my notes, this is called T1, so I'm going to stick with that, but you can call it C if you want. Okay, so let me call this Z1, and let me call this Z2, and let me also talk about these inputs. Now this, you can see that it is like an input that we don't directly control. It's the incoming liquid's temperature. The liquid might be coming from the ambient storage, so it may be influenced by the ambient temperature. So this input, we basically call it as, let me again switch colors maybe. So let me call this the disturbance input. Okay, inlet temperature, and this actually is the control input. The heater temperature, right?
Hocam ona çift input olduğu için şey yazamıyoruz mu transfer edilmişti?
Well, that's going to be coming in the next few minutes, I guess, what we will be able to do with this. But at this point, at least, we can see that it is a differential equation model, right? Is it linear?
And it looks linear, but there is two inputs.
Okay, but remember that these two concepts are separate from each other. I mean, it can be linear with single input, it can be linear with multiple inputs, it can be linear with single output, and it can be linear with multiple outputs. Okay? So this one is linear, definitely, and as you said, it doesn't have a single input, it has two inputs. Okay? So it's a linear multi-input system. Okay? Is it a constant coefficient differential equation? Yes. So is it a time invariant or time varying system?
Time invariant.
It is time invariant, right? Time varying systems would have those coefficients over here, over there, you know, there's T1, Z1, Z2. If these become a function of time themselves, then the system would be time varying. For example, if let's say if this inflow of liquid is changing with time, the flow of liquid, then this system would be a time varying system. Okay, because Q will not be a constant, but it's going to be Q of t, a function of time, which will make Z1 a function of time. So this system will be time varying. That means even if you apply the same input, but you apply it with a certain time delay, the output will be different. Okay, with a time invariant system, it doesn't matter when you apply the input, the output will just be a shifted version of the same output that you had before moving or shifting the input. Okay, is there any questions at this point? Okay, so now let me, so this gives us our simplified differential equation. Sorry, I have also plus t of t, and that is equal to Z1 times t in of t plus Z2 times th of t. Okay. So what about the initial condition? Okay. Clearly, T0 is equal to T0 is non-zero. Okay. So remember that this is another challenge in deriving a differential equation a challenge in deriving a transfer function representation. Okay, so can we derive one or more transfer functions for this system? The answer will be yes, and basically I will show you how. But as an outline, right, what we will try to do is we will have to take care of the initial condition. We can do this by defining an operating point, an equilibrium point around which we will derive the transfer function. And also, because this system is not a single input, single output system, we will have to apply superposition in order to derive a transfer function from each input to the output. So in superposition, remember from circuit theory, you basically kill the sources one by one. Here we have two inputs. We will assume one of the inputs to be 0. We will derive a transfer function from the other non-zero input to the output. And we will then kill this input and make the other input non-zero, and we will derive another transfer function from that input to the output. And superposition, because the system is linear, the superposition will allow us to combine those transfer functions and the associated outputs in order to obtain the final output of the system. Okay, so I'm going to try to do that now. So the first thing is to define a steady state. Now, in this case, because this system is a forced or a system with an input, and we have discussed what happens, right? We impose steady state condition. Steady state is when the change in the temperature is equal to 0. That means we have a stationary output temperature is a steady state condition. In this case, imposing this constraint will actually result in a relationship between both of the inputs and the output, but a scalar relationship. Okay, so that is the condition for steady state. Okay, so let me see what happens. So we will impose steady state condition and obtain, let's say, the relationship this will be a scalar relationship, not a scalar relationship, sorry, an algebraic relationship rather than a differential relationship. Algebraic relationship between our, let's say, operating point variables. I call these operating point variables because remember that this will be a choice, because any set of variables satisfying that relationship will be in agreement with the steady state condition. Okay, so let's call our operating values T in OP and let's say TH OP and T OP are operating point variables. These are now constant, right? As soon as we select them, they will be constants around which the system will be operating. The actual temperatures, T in, TH, T, will be time varying, but we will define our so-called delta variables, which will make these variables move around these constants, and whenever they are equal to these constants, those operating points, our delta variables will be necessarily equal to 0. Okay. So once we impose this condition, t of t over tt equals 0, that gives us that we have TOP has to be equal to Z1 times T in OP plus Z2 times T H OP. So that is okay. So this means you have to select around which operating point you will be running the system. For example, if you know that the ambient temperature is 25 degrees, it's out of your control, it's, let's say, seasonal, and you know that you need to regulate the system around, let's say, 60 degrees C. So this one is, let's say, 25 degrees C. That means you will also need to define a heater operating temperature around which the system will operate. And because the heater is your input, you can actually define a constant around which this heater will operate at. Okay?
Can I ask you a question?
Sure. With your name, please.
Ege.
Okay, go ahead.
In this equilibrium concept in general, if we select a variable t in, for example, an equilibrium point, operating point variable, there's only one unique variable that is like for the output, right? For example, if we select 25 degrees and t in and th is something else, like.
Well, you tell me what this equation tells you.
In this case, it's true. I'm asking for general case.
Well, it depends on what kind of equilibrium equation you get. If you have more inputs, obviously there is more freedom, but it really depends on, whether you can define an operating point depends on what variables are under your control. Okay, for example, here, do I have control over T in OP? Most likely not, because this is incoming liquid from some storage area, and that might be, variable, but you can still define, let's say, in a seasonal way, okay, or you can measure it, okay, and then you have a known quantity that you will assume to be constant as you operate your system, okay. Similarly, TOP might be determined by what is the requirement for the outflowing liquid to be. Let's say if you're heating a building and you want to heat the radiators in the building, and you have a setting on the radiators, so that's going to define whether this is 60 degrees or 50 degrees. Okay? And then, depending on those two quantities, now you can define what your heater should be operating at. Does that make sense?
Yes.
Okay. Any other questions? Okay. So that means, this equilibrium equation needs to be satisfied at the operating point. You may have some freedom in how you define the operating point. It may not be unique. For example, this one, really it's a choice. It's a choice whether you will be operating at 60 degrees C. It's a choice, or maybe not that much of a choice, but you can select, depending on the environment, what's going to be the input operating point for the inflowing liquid. And again, the heater temperature is determined uniquely from these two selections. Okay, so in order to obtain a transfer function representation, which, remember, the purpose of which is eventually to derive a controller for the system. If you have a linear system representation like a transfer function, you can define a linear controller for this system. And what we need to keep in mind, based on what we have learned so far, is that this controller will be valid as long as the system is around this operating point. If conditions change, for example, you had designed this controller for, let's say, spring months with a 25 degrees C assumption. If the inflow liquid temperature changes to 35 degrees, you either will need to change the heater temperature in order to have a new equilibrium point. Okay? And once you have that, obviously your delta variables will change. Okay? So you will be operating your controller around a different, in a sense, operating point in order for that controller to still work. Okay? If you design your controller and this is your operating point that you designed the system linear model and then obtain the controller, but the input inflow temperature is no longer at 25 degree but at 35 degree, you are no longer around the chosen equilibrium point. If you use the same controller, obviously things will not behave in the way that you designed them to behave. All right. Okay, so now if we are let's say close enough to this operating point, we have now T0 is equal to TOP, and we can define our delta variables and assume 0 initial conditions. Let me substantiate what I mean by that. So we have T tilde of T will be equal to T of T minus TOP, and we will have T tilde at 0 is equal to 0 because we start operating around the operating point. Similarly, T in tilde of T will be equal to T in of T minus T in OP, and finally we have TH tilde of T again will be around the operating point, THOP. Okay, so these are definitions, right? We define our delta variables. Okay, so that gives us the initial condition being equal to 0 that is required for transfer function representation. Okay, next let us apply superposition so that we can consider each input separately. Apply superposition. So that means we let T in tilde of T equals to 0. That means T in of T is not actually equal to 0. It is equal to its operating value. Okay? So in the delta variables world, any 0 means that you're exactly at the operating point and not necessarily 0. Okay? So we have in this case T1 dt tilde of T over dt plus T tilde of T is equal to Z2 times TH tilde of T. And now let's take the Laplace transform. So I'm gonna have S times T1 plus 1 times T tilde of S will be equal to Z2 T tilde H of S. So that's going to give me a first transfer function h1 of s, and that's going to be equal to our output variable t tilde of s divided by the first input, the heater temperature, and that's going to be equal to z2 over s times t1 plus 1. Okay, so that is one of the transfer functions. So that only models what's going to happen at the output if we had only the heater temperature non-zero. Okay. Similarly, let's th of tilde of t equals 0. In this case, I will have again t1 dt tilde of t over dt. Same here, plus t tilde of t. And that's going to be equal to z1 times t in tilde of t. Okay, take the Laplace transform, and I'm going to have st1 plus 1 times t tilde of s equals z1 times t in tilde of s. And that gives us the second transfer function. That is equal to t tilde of s over, this time the second input, the disturbance input, again the delta variable, and that's going to be equal to z1 over the same denominator, mind you. Okay, why the same denominator? Because on the left hand side I don't have anything that is different. I only have difference in terms of the input, and that only determines the numerator of this transfer function. Now, so what's going to be the output in the block diagram domain? Well, it's going to be two inputs, right? Now, what we have is that I will have t in of t tilde, because I need to operate in the delta variable domain. This input will go through one of the transfer functions, st1 plus 1. And the second input, th of t, will basically go through another transfer function, z2 over st1 plus 1. And those will be combined because of the superposition principle. They will be just combined in order to give us the final output of the system, again in the delta variables domain. So that will be the block diagram representation, block diagram model of the system. Okay. All right. Do you guys have any questions at this point? Any questions?
Yukarıda bir sorun var. T tilde of T, pardon, daha yukarıda hocam. Bir önceki sayfanın sonunda. T tilde of 0 is equal to 0 demişiz orada. T tilde of T olması gerek.
This is the initial condition. Initial condition. Remember, the initial condition is what happens when the time is equal to 0. Okay. Remember, the initial zero initial condition assumption is required in order to derive the transfer function. Otherwise, you get a constant term when you take the Laplace transform, and that doesn't allow you to write the output in terms of the input as a transfer function. Is there any other questions?
I have a question.
Who are you?
Özgür.
Okay, Özgür, go ahead.
When we write the equilibrium point equation around the operating points,
Okay.
we can see that the operating point condition is that there is no change in the variable, the t variable. It's always the case, right? We choose operating points such that there is no change through time in the variable that we.
That's very correct. This is the definition of an equilibrium point, right? This is the definition of equilibrium point. So you start from there.
So by looking at that, can we say that the systems are only controllable when we have certain operating points? I mean, let's say 60 degrees is an operating point for this system, but when it comes to 59, what can we do? Because we designed our controlling system according to an operating point which is 60, but what is the thing that we can?
Well, first of all, remember, if you become kind of if conditions take you away from the operating point, okay, we know that there will be essentially there will be a discrepancy between what the transfer function signifies and what the system actually does. In the case of a linear system like this, there is no linearization, so there is no getting away from the dynamics of the system. But we know that in this case, a constant value will be creeping in. So there will be some kind of a bias in the system. Okay? So that means this 60 degrees, for example, this is actually, this is really, maybe talk about the input, the inflow temperature, 25 degrees, right? This is out of your control. If this becomes 27 degrees, there will have to be some small constant creeping into the system, okay? So what's going to happen is that your controller's response will be somehow having an extra disturbance. But if this is a feedback control system, remember that the feedback control system has the ability to actually deal with also changes or respond to disturbances, okay? Your model will have an inaccuracy, a constant creeping in. Your feedback controller might be able to compensate for that to some extent, but we can say that this is a non-ideal condition. It's not exactly what the controller was designed for. It is similar to having any other changes in any other parameters, okay? Let's say you design this system and operating point is perfect, but liquid density is changing. Okay, so that means there is an extra disturbance in the system. There can be disturbances from many different areas. An operating point disturbance is also a kind of a disturbance. The system will respond to that depending on how that particular controller is able to handle additional disturbances.
Okay.
Okay.
I have one more little question.
Okay.
Let's think that the requirement for the system is like we want the T be equal to 55 degrees, but that's not an operating point. I mean, maybe 50 and 60 are the operating points, but they want us to regulate the temperature at 55. Is this possible? Because that's not an operating point.
Well, that is possible by changing the operating point. How you can change this equation gives you the freedom to do that. Because if, let's say, T operating point is rather than 60, it is 55, now you can calculate from this equation a new operating point for the heater.
But maybe the 55 degrees point does not make the derivative zero.
It doesn't matter because the derivative is assumed to be zero, giving us this equation. So as long as you satisfy this algebraic equation, you know that you enforce the derivative to be equal to 0. So because this equation has more than one variables in it, it is always possible to fix some of the variables and determine another variable that you can easily change. In this case, it's the heater temperature. So you can, in response to a changing outflow operating temperature, let's say instead of 60, you have now 50 required, you can now calculate a new heater operating temperature. You can set the heater around that temperature, and you can use the same model and therefore the same controller.
Okay. I
Okay.
got it.
Let's have a break, and then we will meet in 10 minutes. Okay, so it's gonna be 50 past 10. Okay?
Hocam attendance quiz var mı?
Dönünce yapacağız.
Tamam.
Tamam. Görüşürüz.